The second easiest calculation to do is, actually it's identical to the calculation we just did. What if we had the fully deprotonated species? So we have 0.1 molar, no H's, just A minus. What's the pH of this solution? Using the same arguments we used for that fully protonated form, the only equilibrium that's really going to matter is the first KB1. So A minus plus H2O going to HA plus hydroxide, which will be equal, that's KB1 will describe that. And so this equilibrium is the one that's going to matter. We can treat this like we would a monoprotic base and find the pH, and we'll do that in just a second. Right, we will have the second reaction that can occur where the intermediate form can lose another proton to form, can gain another proton to form H2A plus and a hydroxide ion. That'll be described by Kb2. But this, again, is going to be really small, this Kb2 value, which means it's not going to matter in terms of finding the pH. Okay, so we can set up the same similar sort of ice table like we would for a monoprotic base. Right, so we'll start with 0.1, H2O doesn't matter, 0, 0, minus x plus x plus x, 0.1 minus x, x, and x. And so KB1 will be equal to x squared over f minus x. Okay, so the slightly tricky thing here is we need to know what KB is and KB1. And the thing to remember is that, to realize is that KB1 is, we need to think about which is the conjugate acid of this base, right? A minus is the base. What's the conjugate acid? The conjugate acid is HA, right? If that's what shows up on the other side of the equation. So we need Ka for HA, which is Ka2. So Kb1 and Ka2 are related. We can say the same thing for Kb2 and Ka1. Those two are related to each other. They're the conjugate acid base pair. So if we want to find Kb1 times Ka2 is going to be equal to Kw because they are a conjugate acid base pair. So if we want to find Kb1, it'll be equal to Kw over Ka2. All right. So we have all the things that we need to fully solve this problem now. So we can plug in 1.0 times 10 to the minus 14, that's Kw, divided by Ka2, which will be 10 raised to the minus, let me get my number here, 9.868, right? Yeah, minus 9.868. That's the value of pKa2. So we need to raise that 10 to the negative of that number. So that is equal to Kb1. And that's going to be equal to x squared over 0.1 minus x, right? F specifically is 0.1 here. We can go through and solve this and find that x is equal to 0.00268 molar. And remember, since this is a base, this will give us hydroxide concentration. And then to find the pH, we need to find the concentration of H+, which we can use Kw to do that. So concentration of H+ is equal to Kw over hydroxide ion concentration, which is 1.0 times 10 to the minus 14, divided by the number we just calculated, which gives us 3.73 times 10 to the minus 12 molar. A very small number, as we expect, because this is a base. We can take that number, plug it into the pH equation, and that gives us a pH of 11.43. Okay, so again, this is exactly what you would do for a monoprotic species. We could do the same follow-on calculation. We could find the value of the concentration of the fully protonated form. We're going to find it's a very small number, equal to Kb2. So that's the approach that we take with either the fully protonated species or the fully deprotonated species. The more difficult question to answer, and what we'll be looking at for the next couple videos, is that intermediate species can act as either an acid or a base, and how do we treat it? So we'll look at that in the next video.